Bismillah ar-Rahman ar-Rahim. Welcome everyone. We're going to get started on the 675 course. Let me share the screen. What we're going to do today is just get started on the first research problem. And I would like by the end of this lecture to give you the chance to get started on the experimentation. So basically, I hope that by the end of this lecture, you will be able to get started on some of the MATLAB experiments so that you can basically at least get in the mode for the next lectures, inshallah. Okay. So basically, we're going to go over the artifact removal research problem. And then we're going to try to look at what we have, the design input for this research problem. And then we're going to take whatever we understood from all these and basically get started on one point that would help us or build the ground for us to get started on solving this research problem. First of all, is my voice clear?
It is clear. Okay.
Yeah.
Okay. So basically, the ECG artifact removal, first of all, does any one of you know how to read ECG? As an engineer, do you know how to read an ECG? So if you look at an ECG signal, would you be able to know if it has an artifact or not?
Before, doctor, now we get it.
So you learned how to read ECG?
I read the program to talk of how when we are on job, after that we forget it.
Okay, so basically you got some experience with ECG from your job, okay? But most of the graduates, if you have a graduate of biomedical engineering, do you expect the graduate of biomedical engineering to know how to read ECG or basically detect a problem in an ECG signal?
No, sir.
I don't think so, yes, that's true. It's very difficult for us because actually we're not medical doctors. Usually what we know about is how to design an ECG, how to basically build an amplifier that would take an ECG signal from a patient and basically filter it and amplify it to a particular level so that you can either print it or acquire it inside a computer and display it. Other than that, we don't really know what ECG should look like, apart from the very famous, drawing of the ECG, but which is actually not exactly how it should look like in all the channels. So basically, we don't really know how to basically at least describe how the artifacts would look like. So basically, we have ECG signals with artifacts, and we would like to remove these artifacts. So the logical thing to start with is to know what these artifacts look like, okay? And in order for us to be able to do that, we have to use the services of a medical doctor who would look at ECG signals and let us know which part is real and which part is an artifact, okay? So basically, to start with, the origin of these artifacts is basically just noise, okay? We have noise from different sources while acquiring ECG. And usually these noise sources will be additive. So basically when you acquire the ECG from the patient, you're acquiring this ECG plus another one, another signal. So basically maybe we can just write the equation for it so that we can understand it better. So basically we have the original ECG signal, let's just call it x of t, okay? And this x of t, maybe, or basically this is the acquired signal, is basically ECG signal of t plus noise signal of t, okay? And this noise has many sources. It can be random noise. It can be physiological noise. And it can be colored noise from the environment. Let me explain a little bit about each one of these. First of all, the random noise, if you talk random noise, basically, random noise, does any one of you know how to describe random noise? Or where it comes from? Basically, the random noise, if you have an electronic circuit, okay, at temperature above 0 degrees Kelvin, sorry, Kelvin actually doesn't have degree, doesn't have the degree, so it's 0 Kelvin, you will have noise, what's called white noise, and its origin is called thermal noise. Sometimes it's described as thermal noise. Basically, the electrons inside the conductors of any electronic circuit basically have a certain, you can describe it as activity, or basically they do not really conform to basically just conducting electricity. Actually, they add some random variations to the basically the signal that they are conducting, and basically this looks like random noise. Unless you have the conductors working at 0 Kelvin, you're going to have random noise. So basically, whenever you have a signal, and basically, let me draw it as an amplifier so that you understand it a little bit better. Basically, if you have a signal, an ECG signal, for example, okay, and you enter that into an amplifier, whatever this amplifier does, okay, so basically if you have S of t here, whatever comes out of here will be A S of t, where A is the gain, plus noise. Okay, you cannot avoid it. You cannot do anything to prevent an electronic circuit from adding noise to a signal. So the best thing you can do is basically when you basically try to choose an amplifier with low noise. So basically any amplifier will add noise, but certain class of amplifiers would be basically adding the minimum amount of noise. So basically if you buy what's called linear noise amplifier, low noise amplifier, okay, then basically you will be doing the best job you can do actually in order for you to maintain the what's called the signal to noise ratio of your signal. Okay, but actually it's going to be there, nobody can do anything about it. Okay, are we dealing with random noise in ECG? Definitely we do that, but for random noise you usually have either very basic amplifiers, very basic filters, like we're going to talk about them in a second. We can have them as analog signals in the acquisition, and basically in designing the amplifiers with the lowest noise amplifier that we can get. So basically for random noise, the best thing we can do is basically design the circuit carefully. So basically the solution for random noise is basically better circuit design. And basically this is done in all ECG systems that you can find in the market. So basically this is not an issue because we all know that it's present, and basically there's not much we can do about it beyond what we can do in the circuit design. So if you have an ECG system and this ECG system is already designed, of course, basically you can't really improve the random noise beyond what was done in that design. So basically we're not dealing with that in this problem. We're not dealing with the artifacts from random noise in our problem here, because this is basically, this was already too late. You're having a signal from an already built ECG system, and basically you have nothing to do about the circuit that it contains. So we're not talking about random noise. The other class, which is basically, let's consider first maybe the colored noise first. because actually the colored noise is basically some of the things that you find in the environment. So basically the colored noise, let's write it in a color so that you can remember it. This depends on the environment, meaning that if you have AC and this AC is at 60 Hertz, basically somehow you're gonna get your signal, your ECG signal, plus a signal that is 60 Hertz superimposed on it. Okay. Basically, if you remember at the lab, if you worked before in the lab with the oscilloscope, if you don't really put any signal, if you just get a resistance across the terminals of the oscilloscope, you're gonna see the AC right in front of you on the oscilloscope. This is because basically you have wires everywhere in the lab, and these wires carry the 60 Hertz signal, and basically by basically emission, and basically you're gonna get some component of the 60 Hertz in any signal or any circuit that is not shielded enough from the 60 Hertz. Okay, so basically this is colored noise. Why? Because basically when we talk about white noise in the example above, basically when we talk about white noise here means that if you look at the frequency spectrum, if you take this frequency and the power of the noise, you're gonna find basically it contains all frequencies. That's why they call it white noise, like the white color, the white light. White light has all colors, okay? So basically white noise comes at all frequencies, okay? For the colored noise, we call it colored because basically it's concentrated at a certain frequency. So it has a certain color. It's not really a color, but actually you just look at the similarities between the light and the signal, the frequency, because the red and the blue and the green all have different frequencies, okay? So basically, it's exactly the same here. When you have AC, when you have 60 Hertz, then you know that you have colored noise because it has certain frequency. So it's concentrated in a particular frequency, not all the spectrum like the white noise, for example. So basically, for colored noise, this is basically a problem of the environment, okay? And basically, if you know that you have 60 Hertz, you have to make sure that the environment is shielded so that when you put an ECG signal there or an ECG system there, it doesn't get contaminated with the 60 Hertz that is present. For example, if you forget about the ECG, if you worked in a hospital, if you look at something like the EEG, if you have an EEG in your hospital, you know that the room where the EEG is located must be shielded because EEG signals are very low, and if you have contamination from the 60 Hertz, you're gonna have a big problem. So the colored noise is basically a problem of the environment. Usually when you know that you're going to work with 60 Hertz, you add to your system also, you add a filter that allows you to remove the 60 Hertz, okay? So basically the environment, you can put shielding there, and filter, you can put a filter inside the ECG system, or basically when you buy an ECG system or an EEG system or whatever, you make sure that it contains a filter for the AC mains frequency that you have, okay? So basically, these two types, the white noise and the colored noise, they have a particular characteristics that is different from physiological noise, is that they are present all the time. So basically, this will be present all the time, 100% of the time will be there, and this also will be 100% of the time it will be there. Because basically, for the white noise, you're using electronics at a temperature of above 0 degrees Kelvin. 0 degrees Kelvin is minus 273 degrees Celsius. So basically, you'll never be able to work with or get anything basically even near that temperature, okay? For the colored noise, as long as you have wires running in the room where the ECG is located. And basically, you're going to definitely have color noise, basically of 60 hertz. The level of that noise will depend on how the environment is shielded and how effective the filter inside the ECG system is designed. Okay, but they are both basically present all the time. The physiological noise is a little bit different. And basically, the physiological noise is basically what we're going to be dealing with in this project, because the physiological noise has the characteristic of being, let's say, basically intermittent. Sometimes it's there, sometimes it's not. So it depends on the patient, it depends on the connection to the patient, things of that sort. Okay, so all kinds of problems can happen between one patient and another. And they are very tricky because imagine that the doctor complains about the ECG having an artifact, and you go and basically test the same system on a different patient, you don't see anything. And the doctor says that basically I saw an artifact, but I don't see it now. Okay, so it's kind of very tricky because basically it depends on the patient. Okay, so it's kind of difficult to design, to have a particular part of the design made, because basically it differs from one patient to another. So basically the physiological noise can come from different things. First of all, the other physiological signals, like for example, if you have EMG, if you have electromyogram, if you put your electrode near a muscle, and basically if the patient moves that muscle, you're going to have definitely an EMG artifact, EMG superimposed on your ECG signal. The problem with EMG is that the amplitude of the EMG signal is much larger than the ECG signal. Okay, this is a big problem. You can have something, basically you can have other things like EEG, for example, but actually EEG has very low intensity, so basically it doesn't really cause any problems for us because ECG is much stronger. But the EMG is definitely a problem. Another problem for physiological noise is basically if you have motion. The patient motion, basically the electrode interface that takes the signal from the patient to the ECG system, basically it has a model. This model has a resistance and a capacitance. When you have motion, this model gets perturbed, it changes. Okay, so basically it changes the magnitude of the signal, and basically it changes the magnitude depending on the motion, which basically causes an artifact to appear where basically in certain locations the intensity is higher, certain locations intensity is lower, so basically it's a problem. So basically you make changes to the ECG signals that are not dependent on the actual signal that comes from the patient. So this is a big problem. Okay. There is another problem that may come from electronics or may come from the interface itself. It's called like baseline wonder. If you remember also what you did in the lab, sometimes you have a signal and this signal appears nicely like this. Okay. Sometimes you see that basically this signal, you have your own signal, the signal that you want to work with, okay? Like for example, if you have something that would look like that, maybe I should take it somewhere, that's fine. Basically, you're gonna have a very slow moving baseline, and basically your signal is superimposed on that baseline. It's not superimposed on a baseline that is fixed, okay? This can happen because of several things actually, but usually you have like a capacitive effect somehow, and basically it's related to the way the system is designed and the way the electrode is to the patient. But the problem with something like this is that we have a problem when we try to interpret the ECG, because sometimes in order for you to diagnose or for the doctor to diagnose the ECG, he looks for the level of particular segments of the ECG signal. So if the level is elevated, it can basically be a certain disease. If it's depressed, then it's another. So when you have a baseline drift like this is a big problem. Okay, so basically these three types are the three types we're going to consider. Okay, and basically we assume that the model of the noise contamination is linear model like this, like additive noise like this, and so we are going to try to design filters to take care of that. Okay, do you have any problems about? You understand what I'm saying?
It's okay.
Okay, so basically, as you see here, what we're going to talk about, we have different noise sources. As we're talking about, first of all, the baseline wonder. We're going to talk, basically term it BW. Going to talk about muscle problem, which is EMG, and basically we're going to talk about basically this EMG artifact is basically going to be termed MA, muscle artifact. And you have the electrode motion, which is going to be basically EM, which is electrode motion. So basically these three artifacts are really very tricky. So basically you have a database, people created database with signals of each one of these types. And they basically, in order for people to understand how the artifact looks like, they basically give the actual signal, the true signal, and the signal with the artifact, so that you understand the difference between the signal with the artifact and the signal without the artifact. Okay, so basically what we're going to try to do is understand first the type of artifact, and then try to get started on filter design, digital filter design, in order for us to be able to basically remove this artifact. Okay, so the design input that I gave you for this problem is just basically a set of ECG recordings containing these types of artifacts and the original noise-free ECG signal. So basically you have the first type, second type, third type, and the noise-free ECG signal. Okay, and basically from these two, we're going to try to understand exactly what the artifact looks like, and when we know exactly how it looks like, then we can get started on designing a digital filter that would allow us to do that. Usually, first of all, we determine that the signal is additive. We're going to need a filter to be able to remove it. And basically, this leads us to basically the tool itself. The digital filter design is a tool. Okay? How many of you know how to design digital filters? Anyone knows? If you know, just let me know if you know how to design digital filters. Okay? Nobody? None of you know how to do that? So basically, first of all, we determined that we need a filter. And since we're going to do it on a computer, then because the signal is digital, we need digital filter. So basically, we need the theory for this. We need to know how to do that. Okay. Number two, in order for us, if you basically learn how to design digital filters, should we just go ahead and try it on the signals and that's it? Actually, in order for us to make sure that we know what we're talking about, know exactly how to design the digital filters, we're going to basically try the digital filter on something we know. This is the best way to learn things. So basically, if I wanted to amplify a signal, okay, design an amplifier, okay, I basically try or test this amplifier on a sinusoidal signal, okay? Why do I do that? Because basically I know the sinusoidal signal, how it looks like. I know if it gets amplified, I can detect the amplification from the amplitude. I can actually look at the sinusoidal signal and see if the filter or the amplifier did any modification to the signal or distortion to the signal, because it's actually, I know how it looks like. So basically this would lead us to something called simulation. Basically, we're going to simulate signals and make sure that the digital filter we design works with these signals. For example, if I wanted to design a low-pass filter, you know how the low-pass filters look like, okay? You know low-pass filters? I would assume that all of you know low-pass filters. What does a low-pass filter do? Can you hear me?
Yes, doctor.
Okay, a low-pass filter, basically it has a cutoff at a certain frequency. So basically you have, for example, you have cutoff frequency FC. If you are below FC, you get cutoff. If you are above, sorry, it's exactly the opposite. Okay. If you are below that frequency, you get passed. If you are above, you get cut off. Okay, so basically what I can do is basically design or simulate two signals. Basically, if you have a signal like a sinusoidal signal with frequency 10 Hertz and another with frequency, for example, 30 Hertz. Okay, two signals, the signal 1 and signal 2. Okay, and then I design a filter with a cutoff frequency of, for example, 20. What should I expect if I pass the summation of these two signals to that filter? What would happen? If I pass the signal of 10 Hertz, what would happen? To pass, right?
Yes.
Yes, and if you pass the 30 Hertz, it should not, right?
No.
So basically, if we do that and design the low-pass filter with 20 Hertz and it works, then I know that I actually knew how to design a low-pass filter. If I want to do the opposite, if I want to pass this one and
high pass filter,
we use high pass filter. So basically, this is basically a test of how we design digital filters. If we know how to do that, then basically we can actually proceed to understand the characteristics of the artifacts and see whether they will need a low pass filter or a high pass filter. So basically, once we get past that simulation step, we here know how to design a digital filter. Okay, so basically the third step is to look at the artifact. And basically, by looking at the artifact, I would like to basically estimate the properties of the digital filter, or maybe I should say specs, maybe I should write it in color. The specs of the digital filter that we would need. So for example, if I have a certain artifact that looks like it has high frequency, okay, then in order for me to remove the high frequency, I would like to have a low pass filter. If I have an artifact that looks like a low frequency signal, then I would need the opposite. I would need a high pass filter. Okay, if there is an artifact that has both characteristics, then I might be basically thinking about band pass filter. Okay, so basically we're going to look at the artifact. I'm going to show you how to look at the artifact, and basically from what you see in the artifact, you try to estimate where you should go with the digital filter. After that, you get started with designing or basically applying things to the new filter. So after you finish that step, So basically, what you're going to do is basically you're going to apply the filter to actual signal. And see whether it works or not. And this will likely involve experimentation. Meaning that it's not going to work first time. You have to adjust it a little bit. Okay, so basically you have to use experimentation in order for you to be able to optimize the filter characteristics. You get something that is rough. You need rough estimate here from this part here. Because basically I told you that a low pass filter would work. Low pass filter, you can start from 0.001 hertz low pass filter to maybe 1 gigahertz low pass filter. Okay, where exactly do you start? Okay, you have to get a starting point. When you look at the artifact, you're trying to get a starting point that is as close as possible to what you would actually end up using. After that, you optimize it using experimentation. After the experimentation, what you need to do is basically evaluate the experimentations. So basically, you try to basically select or optimize based on certain criteria. So that when I ask you why you designed the filter that way, why you chose the specifications of the filter that way, you tell me that I optimize this particular criteria. Okay, and basically this is how people do it actually in research. Okay, because there are so many different filters. Each one of the filters that is available would actually optimize a certain criteria. Okay, so basically we're going to talk about how to evaluate these criteria, or basically how to which criteria first of all are important, and how to actually try to implement one of these criteria so that we can evaluate our experiments based on it. Okay, so basically this is like the roadmap. Do you have any questions about how to proceed in solving this problem? So basically, as I told you before, we need to learn about digital filters, how to design them, how to apply them. We need to do some simulations in order for us to make sure that we know how to design digital filters, because this is the main tool we're going to be using to solve this problem. So basically, we want to make sure that we understand it first before we apply it to our problem. If you don't do that, by the way, sometimes you end up with results that don't really look good. Okay, and the problem is if you don't really, if you're not confident about your digital filter design skills, then the problem may come from the poorly designed digital filter. You didn't know how to design the filter, or it might be the specifications of the filter that need some improvement a little bit. Okay, so you'll never be able to discriminate between these two unless you make sure with simulations that you know how to design a filter. You're not going to be sure how to evaluate or where the problem that you might end up having may come from. Okay, so we're going to do simulations to be able to verify that we know how to design digital filters, and we're going to look at artifacts, basically the artifacts that are present in the signals, and basically try to or basically estimate the specifications of a proper digital filter that would work well to remove the artifact. And then we apply to actual signals and evaluate. And basically the goal is to optimize. Is that clear?
Yes, clear.
Okay, so basically let's get started on the codes, the MATLAB codes. Okay, first of all, in each one of the research problems that we have, I give you some data and some initial code in order for you to be able to start or get started with your data. Let's get started with that. So basically you have that, basically all these things are the things that I put on Blackboard for you. So basically the part with the data here, what I'm going to do is just unzip it. uncompress the file. So basically, I'll extract it here. So basically, you have an ECG signal or ECG folder right there. Please do exactly as I'm doing right now. So basically, after this lecture, please try to basically repeat exactly what I did and try to work a little bit more so that you can understand what we had, and also generate questions if you have questions. Okay, so it has several images. It has two MATLAB data files. .mat is a data file, a MATLAB data file. You have a certain code here. It's called ECG demo. Okay, so basically I have MATLAB here. I'm going to open new scripts. Basically, all you have to do is just drag and drop this here. Okay, so it's right there. Okay, so this code apparently opens the data files. The data files are S118.mat and S119.mat. Load basically what it does is basically loads whatever is in these data files and put them in the workspace, the MATLAB workspace. And then all that happens after that is just basically drawing the signals, different signals that are present in the MATLAB files. Let's just run it first. Change folder. You have to do that because basically if you don't change the folder, then when it tries to load the data files, it's not going to find them. So when you change the folder to where everything is, the data files will be exactly in the same folder as the code. So I'll change the folder. So basically it's going to draw the different signals. So basically here you have, for each one of these figures, you have 6 figures. For each one of these figures, you have basically the original signal, the signal with the EMG noise, for example, and the difference between these two, so that you know how the artifact would look like. Let's go for figure 1 first. Magnified. See here, this is the original ECG signal. So basically, this is acceptable. But as you see, you can see actually for electrode motion, you basically see here some variation. But actually, with electrode motion, it's much. Basically, sometimes you see things that are not present in the original ECG signal. So basically, you look at the difference, basically it looks really bad. Okay, so basically this is the original, this is the one with the noise, and this is the difference. Please note the magnitude for each, by the way, so that you don't get them confused. So basically, this is not as large as the ECG signal. It's basically the small variations that you see here are the ones that are here. So you have noise levels from -200 to 200, while the signal itself is between basically from 400 to basically the peak to peak would be 1000. Okay, so basically just to put it in perspective, this is basically you have two different signals, signal 118 and signal 119. Let's get signal 2. Okay. Signal 119 is acquired from a different place. So basically it looks a little bit different. The ECG signals, they don't really look like ECG, the regular ECG that we know that basically we saw here in the first one. This looks like the regular ECG that we're used to. Okay, but actually if you take the ECG signal from a different location, you will have a different ECG shape. So basically, this is like a different location, so that you know, or a different patient, okay, so that you know how the artifact would look like from basically a different patient or from a different location, because basically it's not going to look the same. If you look at this signal here and this other signal here, it might not look exactly the same. So this is basic electrode motion, and it looks really difficult. If you look at this one here, this is the one that we're going to start with, which basically contains the baseline wander. So basically, as you see here, the signal basically is the ECG signal seems to overlap a certain baseline shape. You have a shape that looks like this, basically. And basically, your ECG signal is added to that, which is not good. this is the original signal. As you see, it has some variations, but they are acceptable. Here, it's not acceptable. Okay, so basically, you should try to get it at least to be like this. Okay, if you look at the one from signal 119, it looks like this. Okay, so basically, it's very obvious that basically it changes things in the ECG signal itself. For the third artifact, which is the muscle artifact, it looks like this. So basically, if you look at this, basically, in order for you to see that here, look at this one here. It looks clean. Here, it doesn't look clean. Let me show it to you a little bit. Let's just try to. See, for example, here, it looks much smoother than here. Here, it has very small variations. Here, the variations are much larger. Okay, so basically, this is very clear here, actually. Okay, so basically, EMG is usually the range of EMG signals is usually it starts from the same frequency range of ECG and goes all the way almost 1 kilohertz or even more. It depends on the kind of motion that is produced by the muscle. So basically, as you see here, it looks like high frequency noise. So basically, if you take this part here, if you magnify it, it varies very quickly. So basically, this looks like a high frequency signal. If you look at something like, for example, this one here, magnify this. Actually, no. So basically, it has very small variations. Basically, if you look at the actual signal itself, it varies very widely. So basically, it varies very slowly, okay, in this particular artifact. Okay, so basically, it's very clear that this is a low-pass artifact. For the other one, the third one here, sorry, this one here, this is a high-frequency artifact. And for the other one, for the first one, actually it's complicated. It has both, basically. It's obvious that it has baseline variations and also has high frequency variations. So basically, we can say that basically this has both. So in order for us to basically think about that, basically, we're going to talk about that in detail in probably next lecture. Basically, how to basically try to design a filter or estimate the filter specifications that would allow us to remove each one of these different types. Okay? Is that clear?
Yes, sir.
Okay. Yes, yes.
Okay. Okay, so basically what we are going to do now is get started on the design of digital filters. Okay, you never had any experience with digital filters in your signal systems course? You never had any experience? None of you had a signal systems course? Okay, so I assume that none of you had any digital filter design experience. Is that correct?
Yes, sir.
Okay. So I don't see Reno still. I was hoping that Reno would be here by that time so that we can get started on the digital filter design with him, but it's fine. It's fine. So basically what I'm going to do now is get started on the part where we use MATLAB to design digital filters. Okay? So basically, MATLAB has a unique tool for designing filters. Basically, it's called Filter Designer. It used to be called FDA tool, Filter Design and Analysis Tool. I think in the new version, they call it Filter Designer. Are all of you have, does anyone, basically, do you all have MATLAB by now, right? You all have MATLAB or not?
Still share the lessons.
The what?
It's easy to get it.
I can hear you clearly.
The
I'm sorry.
lessons.
You still have the
The
problem.
license.
From last time, I mentioned that if you have a problem with the license, it means that you don't have MATLAB. Okay, so this is a problem. Okay,
Yeah.
so you need to find the what? You have MATLAB?
No, sir. We try to get it, but the problem with the license. That means we don't have.
I'm not sure exactly what to tell you, but actually it's a big problem. If you don't have the license, then you cannot work with MATLAB, right? So what can we do? Can't you get a copy from someone?
We will be try to get it.
You're still you're not successful in doing that?
I search for it, sir, in my area. I can't find it.
I mean, from other students. I'm not talking about going to a bookstore or something like that. You're never gonna find in there. I mean, from the other colleagues in the department or the program.
Yes.
You ask them.
Yeah, I asked.
You should.
نقدر نحصل عليه يا دكتور. أنا عندي نسخة 2013.
2013 will be a little bit old, but
الحين عبد الكريم 19 و20 13 بتكون قديمة ما راح يكون فيها جميع.
هي اللي شغالة عندي.
Okay, this is a major problem because actually I was hoping to get started on this now, and you go home and or basically after the lecture you repeat what I did. So I'm not really sure what to do, but I'm not really sure what to do. But let me get started with this. But it's a big problem, actually.
دكتور
Yes, go ahead.
حتى بعض الاي تيز وكذا تكون نسخة مضروبة أصلا.
Yes. What we're talking about is a cracked version. It's not a real version, not an official version, because basically we have no way of obtaining an original license. I'm not sure about the student version. Some people said that you can get a student version of MATLAB for like $29, something like that. I'm not sure if you can get access to that. Reno was planning to do that. I'm not sure if he did or not, but you can ask him.
The program with Reno, it is the same program with me. We exactly worked on it last semester. And the lesson is off. It's the same program, you know. If he, I will be call him. If he touch that one by 20 by 30, it's not matter. We can't pay for it.
Okay. No, I mean the original version. The student license is very cheap. It's not expensive. I'll tell you what, basically I'm going to go over the MATLAB things. Maybe I can ask someone, can you hold on for 5 minutes? I can call someone and check if he has a license or not. Okay? Can you hold on for 1 second, for five just 1 minute? Yes.
Sure.
Doctor, I have a cracked version, but the problem is it's about 26 gigabyte. I don't know how to pass that copy to my friends.
So you have a copy of 26? Oh, okay.
Yeah,
it's very difficult to upload. You have to get it in person. Okay, let me try, because actually I know of a version that's a little bit smaller than that, and maybe we can actually post it somewhere. Just give me 1 minute. I'll call someone and get back to you. Okay, just hold on. Okay.
Okay.
Okay, I think we can get the 2017 version for it's about 11 gigabytes. So it's a little bit smaller than that 26 gigabytes for the later version. Okay, so 2017 should be okay. Okay, so basically I'm gonna try to get that copy, that 2017, and basically upload it somewhere and send you the link to download, and I'll remove it quickly after that. Okay.
Okay. Okay.
If it doesn't work, maybe 11 gigabytes should fit within the Google Drive size. So basically, it shouldn't be a problem. For the 26, I think it's above the Google Drive limit. So basically, hopefully this will solve the problem. Okay. So basically, hopefully I'm gonna do that today, inshallah. Okay. I'll send you the link, and basically let me know if you have any problems. Usually the link is in the at least the one that I discussed with the person. Basically, it comes .iso. It comes as .iso file. Okay, .iso opens with WinRAR, just like any archive. Okay, so basically it has two ISO. Basically, is what you make to basically burn on DVD. Okay, so basically ISO is the if you have a DVD, so basically you can actually put it in the form of ISO, and basically so you have DVD 1 and you have another one for DVD 2. So what you would do usually is basically start with this one, and you will have the installer there. Okay, and then when the installing program asks you for inserts DVD 2, you basically unzip this file, okay, or uncompress this file in exactly the same location as DVD 1. Okay. If you have any problem, basically look at the there will be like a location where you see or an explanation on how to basically install that version on that same DVD 1. That clear? Is that clear?
Yes. Okay.
Yeah.
Okay. So now we're going to get started on the filter design and the simulation, and then hopefully by the time you basically get started on these experiments, maybe tomorrow or something like that, you'll be able to have the MATLAB and basically get started on repeating what I have here in the lecture. Okay. So even if you have the MATLAB after 2-3 days, it's gonna be still okay. You can look at the video of the lecture and basically follow what I have there. Okay, so I'm going to start with filter designer. Filter designer. Okay, filter F small. Okay, you notice that filter designer, filter F small. Okay, so filter designer. Okay, close. You have an interface that would look like this. Basically, the filter has certain characteristics, any filter, okay? For a low-pass filter, for example, we're gonna start with a low-pass filter. Basically, whenever you select the filter type here, this is low pass, this is high pass, this is band pass, this is band stop. And basically, we have two different types of filters, FIR and IIR. What I'm going to do now is I'm going to show you a demonstration of how to design a filter and how to apply it to a simulated signal without getting into the theory at all, okay? And basically, when we feel comfortable designing the filter without even knowing the theory behind it, I'm going to explain the theory, and then you will feel that basically you will know the theory much better when you actually try things and know how the outcome would look like. So in order for you to design a low-pass filter, you have to design, basically you have to have a certain cutoff frequency, which is called F-pass. Unlike the ideal filter that we talked about in the, let me just close all the, basically, unlike the part or the design that we talked about in the theoretical context, like basically we assume that the low pass filter looks like this, okay? What we call brick wall filter. Brick wall, like a wall, basically. You have a filter that basically you have, if you have a frequency here, it would pass, here it passes, here it doesn't, immediately after. So if you have a cutoff frequency of 10 Hertz, then 9.99999 would be okay. 10.00001 would not be okay, okay? This is not practical, okay? Practical filters basically look a little bit different. Basically, they have a smoother transition from the pass band to the stop band. Stop band basically where basically you remove the signal. Here the pass band where the signal passes. Here the signal doesn't pass. Here basically in the middle between the two, what we call transition region. Okay, and basically it starts from what we called F pass here, and we call this F stop. Okay, so basically F pass, the first frequency is the limit of passing. The F stop is the start of stop. And the transition zone here ideally would be 0, but it's never 0. In practical filters, it's never 0. And I'm going to show you the effect of designing the filter to have almost 0 transition zone. The second thing about the practical filter is that usually in the pass band, it's never flat like this. It's never like 1. It's never like this. It can actually have some variations around 1. And basically, instead of having just 1 here, you allow it to change here within a certain limit. Okay, so you allow certain range that is acceptable for the variations. For example, I can say that it's 1 plus minus 0.1, 0.01 to be okay, to be actually better. Okay, so basically it's 0.01. Okay, I'm accepting a tolerance in this one. For the stop band, you actually need to define what's called minimum attenuation. So basically, you have to have a certain level of depression or a certain level of suppression of the signals in this band. So basically, I can say that all the signals in the stop band must be multiplied by at least 1 over 100 or 1 over 1000. Okay, it means that if you have a signal, if you have noise, okay, in this range, it will be multiplied by at least 1 over 1000 or at least 1 over 100. Okay, so basically, in order for me to design a filter, I have to have basically the f-pass, f-stop, attenuation, or the pass band tolerance, and the stop band attenuation. Okay, let's go and look at the filter design tool and basically apply that practically. This is the filter designer basically. Here, the tolerance of the pass band. Here, the attenuation of the stop band. Here, f-pass, here, f-stop. Let's assume that we're going to repeat just the example that we're talking about. We have 2 signals. One of them is 10 Hertz. The other one is 30 Hertz. I would like to separate these 2 signals. So I would like to design a filter with a cutoff frequency or a pass band frequency of 20. So basically, I'm going to start. First of all, you have to have the sampling frequency. Otherwise, it's not going to be able to do anything. So basically, let's assume that we have a sampling frequency of, for example, 200 or 300, whatever, 200 samples per second. The f-pass here, I'm going to say that is going to be 20. Okay, the f-stop means that this is the level basically at which or beyond which the attenuation that we are going to define will apply to all the input signals. So basically, I'm going to say, for example, 25. So basically, after 25, including the 30 Hertz that I'm going to want to filter, okay, basically will start at 25. Here I define the pass band attenuation and pass band tolerance and stop band attenuation. Usually people in the filter community, digital filter community, they are used to decibels. So for example, when we talk about the cutoff frequency, we say that it's a 3 dB point, 3 decibel points, okay? So basic decibels are more common, but actually if you want to have it in linear range, you can actually put it like this. So basically it's here, it's 0.1, which means that the signal would be 1 plus minus 0.1. If you want to have it 0.01, you can have it 0.01. Here, the stop band attenuation is basically 0.001, meaning that any signal with frequency in the stop band will be multiplied by at least 0.001, so 1 over 1000. Okay, let's try to see what this filter would look like, and basically then try to think about basically the different parameters here, and basically try to see if you understand what we're doing or not. So basically all I have to do is just come here and say design filter. Looks like this. This is basically the characteristics of the filter. basically you see here some very small variations. You see here variation, but actually all of them, basically the magnitude here is decibel. Decibel, if you have 1/1000, it's -60 decibel. So here you see that all the parts in the stop band will actually be below 60 or -60 decibels, which basically satisfies this. Okay? So basically this looks like a good filter. Basically you start with 20 here. This is a cutoff frequency. 20 looks okay. And 30 or 25, basically you start the stop band. So basically at 30, you're sure that will give you blind by at least 1/1000. Are these specifications the best we can do? Actually, no, because basically the order here, if you look at this part here, can you read the text? Can you read the text, please?
Where this one?
Yes.
Direct
order?
FIR
102. The order is 102.
stable,
What
yes.
is the order? The order is basically the size of the filter. Basically, just to give you an idea, if you're assembling a digital, if you're assembling an analog filter in the lab, if you have an RC filter, remember the RC filter? You have a resistance and capacitance. This is basically a low-pass filter, okay? The RC filter is an order 1 filter. In order for you to have an order 102, 102, you have to have 102 resistors and capacitors. Can you imagine that? Okay, so this is a little bit large. So basically, we're talking about a filter that would be implemented in the computer. So some people might think that we don't really care, okay? But actually, we're going to see that this order will have basically some consequences. And usually, in order for you to implement a filter with an order 102, you're gonna have to do more calculation than a much smaller filter. And basically, if you want to implement that filter to be a real-time filter that is basically working in real time, so as the signal is coming to the computer, you're basically processing and displaying in real time, then this will be a problem. Okay, let's try to see the effect of each one of these parameters. So for example, let's see, for example, if we make the f-stop very close to f-best. So basically, we're trying to make the filter as ideal, as close to ideal as possible. Okay, so let's have that as 21. So this means that this point here will move very close to 20. So basically, you're gonna become basically almost brick wall. Basically, you're gonna have transition that is very steep between 20 and 21. 20 passes, 21 doesn't. Let's try to see if we modify that, what would that affect the filter? Remember that the order here is 102. See how it looks like now? The order now is 509. 509. So basically, just trying to get closer to the ideal filter made the order basically explode. This is not a good thing. How about if we remember that we would like to remove a 30 Hertz signal? So basically, we don't have to start the stop band from here. We can stop it at 29. Let's try to have this as 29. The order now is half what we started with. Instead of having 102, we have now 56. Okay, and still, if you see here, the 30 Hertz will still be attenuated by -60 decibels, which is basically 1/1000. Okay, so basically, this would look like a much more efficient way of doing this. Let's try to improve this also. Let's try to just change it to 0.1 like it was the default value for it. Okay, just basically I'm going to allow variations here within 0.1. Remember that the cutoff frequency, or basically the magnitude at the cutoff frequency, was 1 over square root of 2 of the actual signal. So basically, it was like, it was definitely below minus 0.1 from the original one. So basically, 0.1 should still be okay. Let's see what that would affect, how that would affect the signal. Basically here, you have 0 decibel. 0 decibel means it's 1, because basically decibel is a 20 log the value. So basically 0 is 20 log 1. So basically here in the bass band you have some variation, but actually they seem acceptable. Okay. If you look at the order here, you actually were able to, instead of having 56 filter of 56, you actually went down 16. So basically you have now an order of 40, which is really good. So basically these are ways of optimizing the filter characteristics so that you have the minimum order that you can get. Because actually it's very important. In some applications, actually, you have a limitation of the order that you can use. Because of the real time, if you want to calculate the output of the filter, you have to have it basically with very small order so that you can calculate the values very quickly and post them or display the result right away. Okay, so basically these kinds of things are the things that we're going to be playing with. Okay, and basically let's try this again with the decibel range. Basically in the decibel range, here you have 1 decibel. And here you have like 80. 80 is like 1 over 10,000. Okay, let's go and discuss the decibel scale again. Basically, the decibel scale, sorry. Let me get that color here. The decibel scale is 20 log amplitude. Okay, meaning that if you have want to have the amplitude here 1 over, let's just start with 1. Okay, 20 log 1 equals to what? Log 1. How much is log 1? Log 1 is 0.
0. Log 1.
So it's 0 decibel. Okay, so 0 decibels corresponds to an amplitude of 1. How about if we have 20 log 10?
1.
10. This
20.
is 1. This is 1 times 1, so it's going to be 20 decibel. How about 100?
It become 20 decibel. 200.
20? This is 2, because basically log 100 is 2. Remember that the log is basically 10
power
log. The
40.
number is equal to A. Okay, so basically log 100, yes, this is 40. And the same thing, you can actually see that the amplitude when it's 1,000, it's going to be 60. When it's 10,000, it's going to be 80. Okay? The thing is, if you actually, instead of having the actual number here, if you have 1 over 100 or 1 over 1,000 or 1 over 10, what's going to happen here? What's going to happen here?
Remember that 1 over 10, it's become bigger than 1 over.
Actually, if you just have, for example, log y over x is equal to log x minus log y. Remember that?
Yeah.
So basically, this will be log 1 minus log 10. So basically, this will be what? Minus. Is that clear?
Yes,
Yeah.
clear.
So usually in the filter context and digital filter context, if you look at a paper that talks about a filter, usually it talks about the specifications in terms of decibel, not in terms of linear scale, because actually this is much more commonly used. Okay, so basically in what we saw in MATLAB, we're going to basically we can actually do the same thing in MATLAB. Basically, instead of putting here if I want, for example, 1/1000, I can put here 60. And the one here is okay. I can also put a number that the one should be okay, because actually it's within the 3 decibels. So basically you have variations here for about 1 decibel, and this 60, and the order is about 44, which is okay. How about if we try this? We would like to take this filter and use it. Okay. In order for us to do that, the simplest way, in the same exact filter designer, you have something called export. Basically, export, generate MATLAB code. Okay, you can generate the filter design function. Okay, I prefer if you use that. Okay, just a second. I'm sorry.
Doctor.
Yes.
Okay.
I'm sorry. So basically what I'm going to do now is try to use basically generate the filter, just try to use this filter and basically simulate some signals and try to see if it works or not. So basically here, as I was saying, we're going to use generate MATLAB code, and basically you say you select filter design function. So basically I'm going to select that. I'm going to call it, let's just call it lecture 1 LPF1. Okay, let's call it any name. Okay, what happens is that it's going to open it for you like this. It's going to add it to the workspace, add it to the editor. Okay, so you have here, this is the design of the filter. Okay, and you see here the numbers that you entered are there already. Okay, so basically in order for you to be able to use it, you can either use it as a function like this, but actually the easiest thing is just comment this function and continue your code here. So for example, here I'm going to generate 2 signals. One of them is 10 Hertz and the other one is 30 Hertz. Okay, and then apply that filter to these 2 signals. Okay, again, I'm actually taking you quickly over this. So basically you can actually try things yourself without understanding much of what you're doing, but actually you're going to be trying things. Okay, after you try things, when I get to talk about the theory, you're going to understand it in a much better way. Okay, because actually you know how it looks like, and you will know that basically what to expect or what you will need to know from the theory. Okay. Okay. So basically, I'm going to generate 2 signals now. Okay. In order for us to generate 2 sinusoidal signals, let me go back to the editor, to this part here. I want to know how to generate 2 sinusoidal signals. Basically, the general form of any sinusoidal signal looks like this. Basically, if you have a signal x of t, maybe I should select a different color. Sinusoidal signals are either sine or cosine or e to the power or e to the minus j omega. Okay, so basically they are all the same, but actually let's just take it as sinusoidal. Okay, the general form is twice pi f times t. This is the time version, the continuous time version. If I wanted to get that into a discrete form, what I need to do is basically select the time points that are equal to n ts, where ts here is what? Sampling period. So basically, if you have a sinusoidal signal, you want to take it here, 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 here. Take it in certain points, and actually each one of these points is separated by ts from the next point. So basically, if I use n here, the number n, or the n here is 0, 1, 2, and so on. Okay. If I do it like this, if I basically substitute t here by nts, then I'm going to get a discrete version of x. So basically, this is going to be x of n equal to sine twice pi f, which is the main frequency, or f naught. Let's just call it f naught. This is the frequency of the sinusoidal signal, times n ts. Okay. So basically, all I have to do is just put f naught with whatever I want and ts with whatever I want, and basically have n as 0, 1, 2, and so on. Let's try to do that in MATLAB. And basically, we're going to generate the signal and display it also, just to make sure that we did it right. So basically, what I first will do is basically, let's just put fs, the sampling frequency that we put in MATLAB was 200, right? 200, right? Okay. So basically, this is the sampling frequency. I'm going to try to document the code that we generate here, so that when you read it, when I upload it to you, you understand what it means. This is the sampling frequency, which is the sampling frequency, exactly the sampling frequency that we use here. See here, it's already there. It's already there. So I don't have to put it, actually. It's already up here. Okay. TS is basically 1 over Fs. This is the sampling period. We're going to need that to generate the signal from NTS. And let's take n, or let's take a number of n is equal to, for example, 100. Or maybe this will be 10, maybe 200. Okay. You can actually change it. This is the number of points. Basically, we're going to draw the signal. So basically, we're just going to take this number of points and basically generate them. And change any one of these. And basically, n, small n, which is a time variable, the discrete time variable will be from 0 to n minus 1. This is the discrete time variable. Okay. S1, which is signal 1, let's just call it signal 1, will be equal to sine 2 times pi. Pi in MATLAB is pi, basically, times f. F we can select basically f1 for signal 1 equals to 10, which is 10 hertz. F2 is equal to 20 or 30, which is the second signal that we talked about. Okay. So sig1 is equal to f1 times n times ts, exactly like what we had in the theory. Basically, we're going to do the same thing for signal 2, but just change f1 to f2. Okay, and then say that sig, okay, maybe sig x is going to be basically sig1 plus sig2. Okay, let's draw these. Okay, so basically I'm just going to generate a figure, and I usually prefer to use subplot so that you have multiple plots in the same figure so that you can see all of them. So let's consider that we have basically you're going to draw the first signal, the second signal, the summation, and basically you can have also the filtered after we apply the filter. Okay, so basically the subplot here, we generate a matrix of 4x1 figures inside that figure, and I'm going to draw in the first one. Let's say plot of Sig1. Usually it's better to just use n because actually it's x and y basically for the plot. So n is basically the time variable, so I'll use it like this. So I repeat this. For the second slot, I'm going to draw signal 2. And for the third slot here, I'm going to draw the summation signal. Let's just run it and run that and see what comes out. See here? Is it clear for you? You have the first signal, you have the second signal, you have the summation that looks like this. Okay? What we need to do now is to take this signal here and apply the filter that we designed here. Basically, the filter comes out as HD. Basically, that's a format for the filter. We're going to talk about it when we describe the theory of the filters a little bit more next time. But basically, we're going to need to take that filter here and apply it to the figure, to the signal, this signal here in the figure, and basically come up with a filtered version that hopefully would look like this one here. If you see that basically this is low frequency, this is high frequency, we have a cutoff frequency in the middle. So basically it should completely remove the signal here. And basically we get something that looks like this. Okay, let's try that. In order for you to apply a filter, basically there is a function called filter. Okay, very simple. Let's just say sigf, which is filtered version of the signal, will be filter. And basically you put the filter that you designed and the signal. That's it. Okay, and then what we're going to do is basically just draw it in the fourth slot. Okay, let's try that. So basically here, in addition to just drawing the filters or the signals that I simulated, I'll filter the summation and basically draw the filtered version of the summation. Let's see how that works. See here? What's your opinion about that? Any observations about the output? Is it good? Does it look good? Does it look okay? Does it look like what you would expect from a filter like this?
The beginning from 0 to 20.
From?
0 to 20.
There's a problem here. Yes, exactly. Yeah. This is a transient. Basically, if you remember the circuit problems that you used to solve in your undergraduate, you would remember that you have two components of the response of a system. You have a transient response and you have the steady state response. The transient response is temporary, and basically after a while it dies out, and basically what remains is the steady state response. What we will see together is that this transient response actually is relies on the order. The order of this filter was like the what? Any questions? Okay, so basically, at least in this part, it looks okay. So basically, the steady state part of the filter looks okay, but the first part doesn't look okay. Let's go back. The advantage of using the filter design function here, instead of just using a function, basically we can change the values here. So for example, if I change, if you remember, we had 21, let's take a 25. 25, okay? 25, if you remember, the order of this filter was almost 100, right? Let's try it like this. So basically, I change the stop band from 29 to 25. Let's see what happens.
It's become bigger.
Become bigger. So this is imagine if I actually add it, if I make it like 21, okay? like we did before. See what's happened here? Actually, see, 200 points, and basically didn't even reach the steady state within the first 200 points. Okay, so the order of the filter changes a lot. Okay, changes things a lot. Okay, let's go back and make it like 29, like we used to have it. Okay, and just make sure that it's still okay. I'm going to change now the part about the attenuation. Let's just make it like 0.01 instead of 0.1. Okay, 0.01 instead of 0.001. So basically, let's actually I wanna. Okay, actually here is the order basically. I just wanted to change a little bit. Maybe I can just write it here. And just to see the order of the filters. Okay. So basically, this is a filter now. It has some transient here, but actually, do you see any variation? Do you see any problem here? This is actually a much smaller filter. See here, the transient becomes a little bit smaller. If you remember, it used to be like here. Start here.
Yes, right.
Right.
So basically, it started a little bit earlier. So basically, the order of the filter is smaller now because actually, I made the constraints on the filter, made the demands of the filter a little bit less. So
okay, what happened? 0.1.
Let's try to do that. Okay, we can do that if we make it 0.1.
Please stop. Make it 0.1.
Okay, this is 0.1. Okay. Actually, you might not see it, but actually, let me just make sure. The order now became 19. Okay, so basically, in the figure here, you started from a little bit earlier, even. Okay, than the one before. But actually, if you look at this, the signal actually looks okay. But sometimes, when the signal with the artifact is a little bit larger than the actual signal, like for example, if you have EMG, then you will have a problem with this because actually 0.1 of a signal that is 10 times the actual signal, the true signal, would make a problem. But actually I have to justify or have to basically investigate that by experimentation. So basically, I cannot say that all filters must be at least 60 decibels, for example. No, you have to actually try and see if 40 would work. Okay, and so on. So basically, this is the experimentation part. So here, actually, we saw that we relaxed things a little bit, and we still have a very good signal. So this should be okay. So this is the kind of experimentation that I would like you to do. And whenever we get started with this part, you will have a filter design function like this, and you just keep changing the parameters and checking the output and making sure whether it's acceptable or not. So here, for me, actually, this is very much acceptable. So basically, instead of having a filter with 500, like the one that we saw that we designed from, a short while ago, we actually ended with something that is acceptable with an order of 19, which is great, actually. Okay? So basically, what I would like you to do, just to make sure that you understand what you're doing, basically try to repeat whatever I did. Okay? I'm going to close this function. Okay? But I want you to actually do exactly the same, that basically go all the steps that I did and generate the design function, and then basically try to play a little bit with these kinds of parameters and see what happens. You have any questions about how to do that? And basically you can use these two signals. Basically one of the things that we can do also is just play a little bit with these two signals. Maybe you can make this like 20 and see what happens. So one signal is 20 and the other signal is 30. Okay? It looks a little bit different because basically, you see here, you see some attenuation in some part of the signal. So it's not exactly the same. Okay, let's try to have, for example, let's just take this back to 10 and basically put the other one here as 25. Remember that we have the f-stop at 29. Okay, so basically this is before the f-stop. So the attenuation of this will not be the what we put right there. It's not going to be 0.1. It's going to be a little bit less. See here how it looks like? Because this actually, the signal here actually was not in the stop band. It was basically in the transition zone. When you have something in the transition zone, you will have something that would actually not get attenuated sufficiently to be able to do the proper filtration that you designed. Okay? So basically, let me change this back to 30 and just run it to make sure that it's okay, because this is the version that I'm going to post for you. So basically, this should be okay. So I'm going to post this version for you here. And basically, stop at this point this time and basically start next time with some more experiments with digital filters. And I'm going to explain to you the theory of digital filters, okay? After you actually had the chance of trying things and basically imagining at least the part about the transient. It's very difficult to imagine. If I talk to you at the theory of the transient, you will not know exactly what I'm talking about unless you saw it yourself, okay? So basically next time, what I'm going to do is do some more digital filtering and basically apply the theoretical analysis to whatever we had in the experiments. Okay, so please try to do exactly the same things that we did this lecture by yourself. If you have any questions, please do not hesitate to basically ask me at the beginning of next lecture. We do not have a time schedule or a particular amount of material that we have to cover. The most important thing is for you to learn how to do things. Basically, if you just focus on one topic and learn through that one topic, you know, a lot of tools, that would be sufficient. So basically, we do not have to rush or do not have us to finish a certain topic within a certain amount of time. Feel free to ask me if you want me to repeat things again, it's fine. Okay?
Doctor, thank you very much.
So basically, I'm not gonna go much further this time. I just wanted to get you started on at least some experimentation with MATLAB. And basically, next time, inshallah, we will continue. I don't want to have too many things today without some of you don't have the MATLAB. And basically, hopefully next time, inshallah, everyone will have MATLAB. And basically, we'll have the chance to go through the experiments so that we can continue to build on that a little bit more.
Okay.
Inshallah.
Inshallah. Doctor, can I ask you something?
I can hear you.
Doctor?
Yes.
This is Abdul Karim. I haven't registered this course because a 20-minute conflict with another course. I have been told to change the schedule of this course from Odys. So if you don't mind, and
it's a chairman who can do that. I can't do that. You have to talk to the chairman. You have to send to the chairman about this. Which course?
I will talk him if you don't mind.
No, I don't mind, because basically we have our own schedule. Okay, so put it whatever you want, wherever you want. But actually, make sure that you don't have conflicts with other courses, so that you don't cause a problem for another colleague.
Yes.
Just move as far away as possible. Okay. Just put it in the morning. Okay, just put it in the morning. Okay, just put a schedule in the morning so that it doesn't have any conflict with any graduate courses.
Okay.
So okay. Do you have any questions?
Thank
Please
you,
let
Doctor.
me know if you have any problem with the pace. If you have any problem with how I explain things, any problems with the material you don't have the background for, we can actually at least give me the feedback so that the lecture will be most useful to all of you, okay?
Okay.
So do not hesitate to let me know if you have any issues, okay?
Can we find this lecture on the Blackboard? Sure.
You have problems with Blackboard?
No, we don't have. When exactly we will be find this lecture? Your explanation on the Blackboard. After you finish the
I'm going to post it. I'm going to, you mean the lecture itself?
Yes.
Usually what they say that is that after the lecture, 6 hours after the lecture, the video will be posted. The material, the MATLAB, the MATLAB code, basically within MATLAB and some handwritten notes, basically these things are going to be uploaded maybe tonight. Okay, so basically everything would be, by the morning tomorrow, you're going to have everything posted on Blackboard. You can get back the lecture and the material and the video.
Okay.
If you have any problems, just let me know also. Okay? Okay?
واللي الارفاق بالنسبه للاسايمنت هل يوصلك على البلاك بورد دايركت ولا كيف؟
Yes, everything is on Blackboard. So basically, whenever I will ask you to submit an assignment, there will be an assignment on Blackboard so that you can submit through. Okay? So the things that I tell you, like today, I tell you to experiment with some things. Okay? You do not have to submit them. Okay? Just ask me if you have any questions. Whenever we have to submit something, you will find an assignment where you can submit that particular task. Okay? So everything will be through Blackboard. Okay?
Okay, sir.
Okay.
So I'll inshallah talk to you again on next Friday, inshallah. Okay?
Thank you very much.
Inshallah.
Okay, thank you. Shukran. Shukran. Assalamu alaikum.
Wa alaikum assalam.